All right, so now that we have a better idea of what a priority queue is and some of the basic functions, let's maybe start to think a little bit about the implementation. Now, note here it is going to take us a little bit of time, right? So we've introduced this idea of this particular ADT, and we want to, our end goal, right, is basically to say, hey, I want an implementation of this. It's going to take us a little while to get there. Now, on that road there, right, one of the things I want to talk about, which maybe is a new concept for you guys, maybe is not a new concept, is laziness versus eagerness. So, I have this trace here. Let's take a look at this, right? So I have this trace, and here you can see basically I have my some inserts over here, followed by remove, followed by more inserts, more removes. That's kind of a trace of what's happening, right? So we're gonna go through this, right, and then I'll jump back to the terminology in a second. So it's like, say here, right? The way I read this is I do an insert of P, right? Insert of Q, insert E, remove max. Remove max should give me back a Q, right? So this is in alphabetic order. All right. So this left-hand side here is basically giving me the Q's expected behavior, right? So this is, expected. Okay. So from the user's point of view, right, they're using that kind of that Q concept that we saw earlier. This is kind of what they expect to see, right? I add this stuff in, I do these removes, this is what I get back, right? And then on that last column there is, of course, the size, how many things are in there. So that's what we expect. Now, for us, right, we start thinking about implementing this thing. We basically have different choices on how do we get there. So what we have here, right, is somehow the overall choice, right, of something along the lines of keeping the stuff inside of the queue either unordered or ordered. Okay, we have two big choices here. Now, for the sake of this discussion, we're kind of implicitly assuming that we are doing this via arrays. And I'll just write this over here. So this is an array-based implementation. Well, I should say like a linear array. We'll have to come back to the idea of arrays in a few videos, but for now, it's kind of just this array we can imagine throwing stuff into. And so we're going to suppose for a second that maybe this is how we want to do, right? We want to implement that idea of a priority queue using an array. And again, I have my choices of I could either do it using an unordered array or an ordered array. This is actually kind of a little bit of flashback, right, from when you guys studied, how to search through an array of things, way back in your previous class, right? You're like CSE 205, whatever. It's a little bit of a flashback. So take a look at this trace here, right? Let's say, hey, we're doing unordered. What happens, right? What we can see here, right, is as we do different inserts, we're just kind of adding things in there, right? So it's like P got thrown in there, Q got thrown in there, E got thrown in there, right? Then Q got removed, X gets thrown in, A gets thrown in, right? So we're just adding things to the end there, right? So it's like I have this array, right? This is an array, and somehow, right, maybe, index 0 is over here, right? And then I have all these other slots, right, up until, slot N. I'm just throwing things in the end. Okay, that's fine. That's fine. And what we want to then ask ourselves, right, is we're saying here, hey, I'm thinking about how to implement this. What could I do? I could use an array. I could keep that array unordered. Then we want to ask, right, is what does the performance look like, right? So over here, right, we have maybe this idea of I could have my insert or my del. So maybe ask yourself for 1 second, what would be the big O performance of insert if I use an unordered array? What do you think? Okay, well in this case, if I want to do an insert, this will end up costing me, let's see, this will be O of 1, potentially. If we assume no resize, which let's just do it for now, it's going to be O of 1, right? Just throw it at the end, not a whole lot of work. What about del? What do you guys think the big O order of del is going to be? So here it's going to look something along the lines of N. And the reason for that is that if I'm trying to delete an element, I don't know where in the list it's going to be. So I'm going to have to search for it, right? So I'm going to have to go, up and down this list, this array, and try to find, what is the largest thing, right? That's going to, it's a little bit of work, right? It's O of n to figure out what is the largest thing in an array. So it's a little bit of work there. And this is overall what we call the lazy approach. So I'm making basically my insert very cheap, or I'm being lazy about keeping it sorted. With the knowledge, right, that later on when I do delete, it'll be more expensive, right? It'll cost me n to find it back out. So this is a lazy approach, okay? So basically, you'll hear this word, using different usages, but generally what it means is you're putting off work, right? You're putting off the work of sorting. You're going to do it later only when you need to, right? So it's being lazy about a problem. So this is a general idea. All right, the second thing I want to talk about is the ordered way, right? And the ordered way, maybe you can guess, that's going to be our eager approach. So let's take a look here at the trace again. Notice where we insert P stays the same because, hey, what's going to happen? Insert Q ends up being the same. Insert E. Notice that at this point, this looks a little bit different, right? So I have EPQ versus over here I have PQE. A little bit different. And if I notice as I go through and I do those inserts, it's actually keeping them in an ordered an ordered order, I guess, something like that. So it's a little bit different, right? At the end, what I have basically looks like a sorted array versus this one's unsorted. Okay, so this is a different approach. So again, we'll ask the question, how does performance look? So let me write this in here. So I'm going to worry about insert and then del. All right. So insert. What do you guys think? What will be big O for insert in this case? Well, here insert's going to end up looking like, I think for myself, okay, it'll be O of n, right? Because here, every time I'm inserting an element, I need to go search and figure out, hey, where does it go? So it's going to cost me a little bit of time to find out where it goes each time. Okay. What about delete? What do you guys think for delete? How much time does delete take in terms of big O? Well, here delete is going to be, I guess it'll be expensive too. Inside, I'm always, when I do this, I'm hoping, I hope I get a good performance, but no, not in this case, right? Well, okay, so delete. Okay, delete's a little bit complicated here. So delete, it'll be either big O of n or big O of 1. And what happens here, right, is that there's a little bit of magic in the way we say, what basically, how does it ordered, right? So here, if we're looking at this and we're doing our remove max, well, the largest thing is stored over here, right? So this is largest, this is smallest. So in this example, right, if I'm just editing like the end of it, well, if I want to remove max and x is the max, right, so we're going to be at the end, so I can just clear out that one element, right? So here, right, actually the way it's set up, whenever since I have basically the largest element being at kind of the largest index, well, that's the place I'm working at. So whenever I remove max, it's just like I step backwards. It's like I X out, I cross out that, right? Or I cross out, what's the next one? I cross out P, right? Those kind of just disappear right from the end, and I don't have to worry about moving around any elements or searching for any elements, right? I can just save the index of that and use it. So in this example here, right, it will be O of 1. Now, if it was flipped, if I had my largest over here, right, maybe I'll annotate here, right? So that's the O of 1 approach. If I was maybe less clever, I had the largest over there and the smallest over here, well, that would be O of n, because in that case, right, if I delete the thing in front, I got to shift everything back over, right, to make sure that it's flush with index 0, right? It's all backed up all the way. So yeah, for now, for your kind of your notes and your studying, you can kind of just assume it'll work out like this, right? That you'll have your largest be at the higher index. That way, when you delete it, you don't have to worry about it, right? It just it goes away and good to go. All right. So this video, right, in general, right, we're just kind of want to introduce this idea of lazy versus eager, right? First time, right, we basically had to do the work of finding that element, when we pulled it out. In this last approach we just did to keep it ordered, we spent time, when we put it in, to put it in the right place, right? We put it in the right order, right? So we were being eager about sorting it. Both of those are valid approaches to solving a problem, right? And for us, well, I mean, these are both decent ways to do it, right? If I ask you to implement a priority queue, or also we'll introduce this idea of a heap, you could do it with array, right? You get this decent performance. But really, we'll try to do a little bit better, right? So at the end of the day, what we want is we want a del that's log of n, and an insert that's also log of n. Here, there's a trade-off, right? One of them ends up being fast, one of them ends up being slow, right? And maybe if you do one more times than the other, that will work out for you. But maybe we can do a little better. Maybe we can try to make it always reasonably fast. All right, so that's what I got. I'll see you guys in the next video.